Okay, so thanks for the introduction, and thank you very much for inviting me to speak here today. So I'm going to be talking about joint work with Anne Broadbent, which is about quantum homomorphic encryption for a limited class of circuits, those with low T complexity, which I'll explain in my talk. Okay, so the idea of quantum homomorphic encryption is it's the quantum version of a classical cryptographic primitive called homomorphic encryption. So the idea of fully homomorphic encryption, which was first proposed in 1978, was the following. We want to encrypt some data, so say a classical string x, in such a way that we can evaluate any function f on the encrypted data without decrypting. So we want some sort of procedure, eval, which for any function f will take an encryption of x and give you an encryption of f of x. And f should be given as some sort of a classical circuit, for example, in addition and multiplication modulo 2. Okay, so there were some partial results over the years, including some encryption procedures that were homomorphic for, say, log depth circuits or other limited classes of circuits. And then finally, more than 30 years after this was first proposed, the first classical fully homomorphic encryption scheme was proposed. And since then, there have been a number of improvements, but Jeffery gave the first fully homomorphic encryption scheme in 2009. So we're interested in considering a quantum version of this homomorphic encryption. So in the quantum version of homomorphic encryption, we want some way of encrypting a quantum state such that we can evaluate any quantum circuit without decrypting. So there's two ways that this quantum version differs from the classical version. So one is that we want some way of encrypting quantum information. So this is some kind of generalization. And the other is that we want to be able to evaluate a quantum circuit. So the way this might be different is, suppose we have some quantum circuit for factoring. Even if we're only going to give classical encryptions, we would want to be able to get the quantum speedup for factoring. So consider the classical case. Certainly, this evaluation procedure, it cannot be more efficient than actually computing the function f, since that is actually what it's going to do. So it must be at least as, the complexity of this procedure must be at least the complexity of f. And it shouldn't be too much more. And similarly, for the quantum case, if we give an efficient quantum circuit for, say, factoring, we want to be able to efficiently evaluate that circuit. So we could, of course, factor classically, but we would have to give a classical circuit for factoring, which would be, we think, exponentially larger. So the main differences in quantum homomorphic encryption are we want to be able to encrypt quantum data and compute on that, and we also want to be able to get quantum speedups. Okay, so we know from this 2014 result that it's not possible to do this with information theoretic security. So we want to ask, what could we do with computational assumptions? And so in this talk, I'll give some partial results towards full quantum homomorphic encryption under computational assumptions. So to begin, I will introduce more formally classical homomorphic encryption, and then also talk about the quantum version, quantum homomorphic encryption. And then I'll introduce our three schemes. So our first scheme, which we call CL, is homomorphic for Clifford circuits. And then we are able to extend this to two other schemes. So the second scheme is an extension of the first, where we can extend to circuits that have Clifford and T gates and are at most constant T depth. And then a different extension of the first scheme gives us our third scheme, which is homomorphic for any quantum circuit, but it fails to achieve another important property called compactness, which I will define shortly. Okay, so to begin, I'll define a classical homomorphic encryption scheme. So a homomorphic encryption scheme is a four-tuple of polynomial time algorithms. The first is a key generation procedure. So this is going to take a unary representation of some security parameter kappa, and it outputs three keys. So a decryption key, an encryption key, and an evaluation key. The second procedure is some encryption procedure, which takes an encryption key and a message M, and it outputs a ciphertext C. The third procedure is an evaluation procedure. This takes an evaluation key and some function f, which we should think of f as being given as a circuit listed by its gates. And it takes some ciphertext C and it outputs a different ciphertext C prime. And then finally, we have a decryption algorithm which takes a decryption key and a ciphertext and outputs a message. Well, we don't know. I mean, it depends what you've done previously. So it outputs something in your message space. Probably not. Yeah, so here, this is how we imagine these fitting together with, you're right, hopefully some f of m. So suppose this is a public key scheme, then we would imagine that Alice generates 3 keys and she outputs the evaluation key and the encryption key. And then Bob uses the encryption key to encrypt some message M of his choice, and then he outputs the ciphertext. And then Charlie chooses some function that he wants to evaluate on M, and he evaluates it on the ciphertext and outputs some other ciphertext, which Alice can then use the decryption key to decrypt and get, hopefully, f of m. And if we wanted to look at a symmetric key case, we would just have Alice generating keys and also encrypting some message, and then Charlie could then evaluate a function which Alice could decrypt to get f of m. Okay, so there's some properties that we hope such a scheme would have, and the first, of course, is a homomorphic property. So we say that a scheme is C homomorphic, where C is some set of circuits, let's say in addition and multiplication gates. And we say a scheme is C homomorphic if for every f in C, essentially what this says is that if Charlie evaluates with f as an input, then Alice can decrypt and she'll get f of m. So it's saying that this evaluation procedure kind of works for any f in C. The second property we would like is some kind of security. So if this is going to really encrypt a message, it needs to be that an encryption hides the message in some meaningful definition. So one standard cryptographic definition would be indistinguishability under chosen plaintext attack, which essentially says that no polynomial time adversary can distinguish between an encryption of 0 and an encryption of 1. Okay, and there's one other property that we would like to have. So to kind of illustrate why we need a third property, let me show you how we can trivially achieve both of these properties for C, the set of all classical circuits. So this is what I'll call the trivial scheme. So in the trivial scheme, we're going to take any public key encryption scheme. So that's going to have a key generation and some encryption and decryption procedures, but not an evaluation procedure. So for instance, we could take RSA, or we could take something that's actually quantum safe, whatever you like. And now we'll just define another scheme called triv, and its key generation will work as follows. So it's going to use this key generation procedure from the public key encryption scheme to get encryption and decryption keys. And then it's just going to set the evaluation key to 0. And then the encryption of our trivial scheme will just be that it uses this public key encryption scheme to encrypt a message. Okay, so what about the evaluation procedure? So the trivial scheme will have the following evaluation procedure. It's just going to take the ciphertext, and it's just going to append a description of the circuit F. And then the decryption procedure is just going to decrypt C and then apply F. So this is as secure as whatever scheme we started with here, and it's also homomorphic for any classical circuit. We can apply any function after we have decrypted. But this is not at all what we mean by fully homomorphic encryption, because we've somehow cheated. We have put all of the work of evaluating F into the decryption procedure, when in fact we would like this evaluation procedure to do the work of evaluating the function. So this sort of motivates our third property, which is called compactness. And we say that a scheme is compact if the complexity of the decryption procedure does not depend on the F that has been evaluated. So certainly this evaluation procedure, it should be as complex as this circuit here, but the decryption procedure its complexity should be independent of this complexity.
The other thing that the trivial scheme does not do, and which you don't seem to have in your definition when you don't want that, is for the process to hide f. So.
That's true. Yeah. So we actually that's not in this definition. So I guess I would consider that here an extra property that you could have, and we didn't really consider at all whether our schemes satisfy that. That's certainly something interesting to consider, though. Okay, so now we can look at the quantum version, unless there are any questions at this point. So the quantum version is similar. We're going to have a 4-tuple of this time polynomial time quantum algorithms, and so the key generation outputs 3 keys, and we're going to allow the evaluation key to be a quantum state. And we could also have allowed these other keys to be quantum states, but we don't need that, so we'll just suppose that they're classical. And then now our encryption is just going to be, some quantum algorithm which maps some message space to some cipher space. The evaluation is going to take a quantum evaluation key and some cipher state and map it to possibly a different cipher space. And then decryption will just map something in this space back to the message space. And these fit together in the same way as before. And similarly, we want the same kind of properties. So for any set of quantum circuits Q, we'll say that a scheme is Q homomorphic if for every circuit, if Charlie evaluates that circuit on a cipher state, then when Alice decrypts, she gets the result of applying that circuit to the message state.
And two bars mean classical?
Yeah.
Double wires is classical?
Yeah, double wires is classical. So for instance, this will be just a classical description of the quantum circuit. And we also define a quantum analog of indistinguishability under chosen plaintext attack, which just at a high level is that no polynomial time adversary, of course now it can be a quantum adversary, can distinguish an encryption of some state the adversary chooses from an encryption of a maximally mixed state. And then we will also require compactness. So the complexity of decryption should not depend on this C. Okay, so let me summarize our results. And before I summarize the results, let me just show you how you can achieve any 2 of these properties trivially. So first, not encrypting is homomorphic for all quantum circuits, and it's also compact. So you can just evaluate a circuit by just evaluating it, since everything's in the clear. But it has absolutely no security. And the trivial scheme that I showed you before, this is homomorphic for all quantum circuits. And it's as secure as whatever public key encryption scheme we start with. But it is not compact. So the complexity of decryption scales with the number of gates in the evaluated circuit. And finally, the quantum one-time pad. This is not homomorphic, but it's therefore kind of trivially compact, since you can't do anything, you can't evaluate anything. And it's certainly computationally secure. So we can easily achieve any 2 of these 3 properties. So the difficulty is achieving all 3 simultaneously. And here are our partial results towards this. So our first is rather a modest improvement. This is homomorphic for all Clifford circuits. And this scheme is also compact, and it has quantum indistinguishability under chosen plaintext attack security. So this isn't so interesting because Clifford circuits are a rather simple class of circuits, which we kind of think of as the quantum analog of just linear circuits that involve only addition. So our second scheme improves on this, and we get our second scheme is homomorphic for quantum circuits with constant T depth. So this is a slight improvement over just Clifford circuits. And this is also compact and has Q and CPA security. And our third scheme is an improvement in a different way. So it's also an extension of the first scheme. And it's homomorphic for all quantum circuits. However, it's not compact. So the complexity of decryption scales with the number of T gates. In fact, the square of the number of T gates. So this is some kind of improvement over scaling with the number of gates, but it still doesn't achieve this property fully. And it also has Q and CPA security. And just to remind everyone, if we wanted quantum fully homomorphic encryption, we would require all three properties. But we don't achieve this yet. This is still an open problem. Any questions so far?
So the communication between the client and receiver, it could be quantum.
Yeah. So it is kind of different from delegated computation.
So if you take your scheme 3, so complexity scaling is.
So it does require. It is a quantum circuit. It requires just the number of T gates, that number of quantum gates, and if you want the full complexity, including classical, it's the number of T gates squared.
It's not the depth of T gates.
The number, yeah. Okay, and one final remark. Our first and third schemes are public key, and our second scheme is symmetric key. Okay, so now I'll just talk briefly about our schemes. So the first scheme, as I mentioned, it's homomorphic for the class of Clifford circuits. So the first ingredient that we're going to use is the quantum one-time pad. And the quantum one-time pad takes some random bits. If rho is a single qubit state, we would just take random bits A and B and applies this random Pauli. And if rho is an n qubit state, we could think of A and B as being n-bit strings, and then x to the A should be like x to the A1 tensor, x to the A2, etc. Okay, so the quantum one-time pad is essentially just encrypting by applying a random Pauli. The second ingredient that we'll use is this sort of property that defines Clifford. So a Clifford is some kind of circuit that when it conjugates a Pauli, you get another Pauli. So another way of saying that is for any Clifford C and any Pauli, x to the A, z to the B, there exists some other Pauli, x to the A prime, z to the B prime, such that this equality holds. Okay, so that's what it means for C to be a Clifford. This is actually only true up to a phase, but we don't care about the global phase. Okay, so what this A prime and B prime are depends on the circuit C and also the Pauli x to the A, z to the B, which is defined by A and B. So there's some function for every Clifford, f sub C, that will take these A and B to some A prime and B prime such that this is true. And furthermore, this function will always be a linear function. So again, if C is an n-qubit Clifford, then A and B will be n-bit strings, and A prime and B prime will be some other n-bit strings. And there'll be a linear function of A and B that depends on C, the Clifford. Okay, and then the final ingredient for our first scheme, first an example. If P is a phase gate, then we have the following identity. And another way of saying this in our notation is that F sub P maps AB to A, AX, or B. Okay, the final ingredient for our first scheme will just be a classical fully homomorphic encryption scheme. And now we will construct a quantum homomorphic encryption scheme that is homomorphic for Clifford circuits from these things. So to begin with, our scheme, which is called CL, its key generation procedure will just be the classical key generation procedure.
Classical, but secure against quantum attacks.
Hopefully, yeah. And actually, I think all of the fully homomorphic encryption schemes proposed have been based on things that are thought to be quantum safe, so that's convenient. Okay, so we'll just output these three classical keys, and then the CL's encryption procedure will be the following. It's going to take random bits A and B. So if rho is an n-qubit state, these would be n-bit strings, and apply a quantum one-time pad. And in addition to outputting this quantum state, which is the quantum one-time pad of the message, it's also going to output the classical encryption of A and B. And then to evaluate, we'll do the following. We're just going to, for any Clifford C, we're just going to apply C, and then we're going to kind of have this updating of the keys. So we're going to homomorphically evaluate this function, f sub c, on these encrypted keys to get encryptions of A prime and B prime. And then to decrypt, we're simply going to decrypt to get A prime and B prime and undo the one-time pad. So the reason this works, so this will give us the effect of applying this Clifford to the input state. The reason this works is because we've encrypted rho like this. So when we just apply C here, now rho is encrypted by this Pauli. And so when we homomorphically evaluate this function, we recover, when we decrypt, we recover the correct keys. We can decrypt the quantum state. And it's also not difficult, at least, to convince yourself that this is as secure as the classical scheme we've used, since certainly the one-time pad is information theoretically secure, and as long as you can't decrypt these A and B, you still have security. I mean, obviously, the proof is more technical than that, but it's certainly easy to convince yourself that this is secure. Any questions about this scheme? Okay, so now let's try to extend this, this is only homomorphic for Clifford circuits, so we'll try to extend this to a larger class of circuits. So it's known that if you take a set of Clifford gates that generates the Clifford group, and you add any non-Clifford gate, this is a universal quantum gate set. So we can choose any non-Clifford gate, and this would give us a universal quantum gate set. So we will consider a T gate, which has this action for any bit x. And so what this implies is that if we could extend the results to work for any circuit in Clifford's and T gates, we would have fully homomorphic encryption, so quantum fully homomorphic encryption. But we're not going to achieve that because we're going to be kind of limited in the number of T gates we can apply. So if we try to apply a T gate the way we applied a Clifford, by essentially just applying the gate over the quantum one-time pad, it won't quite work, because what will happen is we have this sort of P which needs to be corrected. This is a non-Pauli P. And if we want the evaluator to correct this, it sort of seems that they would need to know the bit A, which is a one-time pad key. And we certainly don't want the evaluator to know the one-time pad key. So we're going to use this kind of gate teleportation idea. So if the evaluator has such an auxiliary state, they can use it to apply P to the A. Since we don't want them to know A, we'll just hide it by applying Z to the K for a random K. And this allows a T gate to be applied through the encryption and gives us another Pauli here. So this is the idea. The idea is that as part of the evaluation key, we'll give some auxiliary states which can help perform a T gate, or more specifically help perform this, correcting this P here after a T gate has been applied. Okay, and the reason that this doesn't work as well as we might hope is, consider a circuit in Clifford's plus T. When we go to apply the first T gate, some arbitrary Clifford has already been applied to the data. And that means that at the point just before this T gate, the one-time pad key here, A1 prime, is going to be some arbitrary linear function of the initial keys. So if we wanted to provide an auxiliary state that looks like this, in general, we would need to know the value of A1 prime. But this depends on the circuit that has been applied previously, which we don't know in advance. So we can't provide this auxiliary state. So we're going to use the following trick. So we can think of these sort of plus states as hiding P corrections. So this hides a P correction of T. If we have a plus state that hides a P correction of T1 and another plus state that hides a P correction of T2, we can turn this into a plus state that hides a P correction of T1 plus T2 mod 2. So that means that if we have some arbitrary number of plus states hiding these different P corrections, we can get this plus state here. Okay, so the idea will be that if we have many auxiliary states of this form, where T runs over all of the initial one-time pad keys, we can make a plus state for any linear function of those initial keys. Okay, so the problem is the reason why we can't extend this to arbitrary circuits is the following. Recall that whatever key appears here ends up as part of the one-time pad key. And the key that we get from adding these plus states contains nonlinear terms. And we don't generally have a way of taking two plus states and kind of multiplying them to get a plus state that hides T1 times T2. So that means that anytime there's a product T1, T2, we actually have to provide another plus state. So we have to provide plus states for all possible products of keys. And things, to make a long story short, things just blow up very quickly as we go to greater depth. So in summary, if we want to do L layers of T gates, we need n to the 2 to the L auxiliary states, where n is the number of qubits. So when I said constant depth before, I really meant depth 1. Okay, so that's our first scheme in a nutshell. So this gives us quantum circuits in Clifford's plus T with constant T depth. Okay, and then in our final scheme, we're going to use the same sort of idea, but we take a slightly different approach. In this scheme, we're going to use an EPR pair to delay correction to decryption. Okay, so this allows us to essentially, at the point of decryption, we're going to run this circuit and measure some k, and whatever we measure here will sort of become a part of this key, and then we'll be able to decrypt. But of course, since we have delayed this until decryption, this gives the decryption procedure some extra work. So in particular, we have to do a circuit like this for every T gate in the circuit that's evaluated. And this gives us a scheme which works for any quantum circuit, but the complexity now depends on the number of T gates. The complexity of decryption now depends on the number of T gates. And so the square actually comes from the fact that later in the circuit, when you measure some k, it's going to depend on sort of previous measurements. So you kind of will have to go through all of the T gates in order and reconstruct certain things which will depend on previous T gates. So the first one will, I think, depend on 1, and the second one will depend on 2, and you'll have to XOR up to the number of T gates things together. So it's only, in terms of quantum computation, it's just the number of T gates, but each of them may be up to the number of T gates classical complexity as well. Okay, so just to summarize, we have these three schemes which get partially towards quantum fully homomorphic encryption, but the problem of quantum fully homomorphic encryption is still open. So I'll just end there. Thank you.
The dependence would only be on T gates on previous levels. The two T gates on the same level will not influence.
In this, I think it is really the number of T gates and not the depth.
Yeah, right. But the T gate would only have to interact with T gate on previous levels. But still, the number of pairs.
But still, okay, yeah, that's true. But by the time you get to the last one, yeah.
Okay, any questions?
Why restrict your group action to be contribution in the first scheme? So like, suppose you have a multiply by any arbitrary matrices. All you need is to preserve the polygroup. So why does that not work?
So do you mean like instead of having random Pauli as the encryption?
No, you have a random Pauli as the encryption, and maybe you apply T on the left, but then you recognize some other gate S that's the reason that your thing works is because conjugation is preserving the polygroup. I'm just saying there's other group actions.
So I think that Cliffords are sort of defined by the fact that they conjugate Pauli's to Pauli's. So I'm not sure that there's anything that would work in general for any Pauli, if that's what you...
Yeah,
Yeah.
I'll ask you more.
Okay, sure.